Hi, this is Chris Galbraith, and today I'm going to be talking about statistical methods for the forensic analysis of geolocated event data. This work was part of my PhD thesis at the University of California, Irvine, and was advised by Smyth and Halstern. It was funded by the National Institute of Standards and Technology, as well as CSAFE, the Center for Statistics and Applications in Forensic Evidence. And a quick disclaimer, anything that I present today is not necessarily the opinion of NIST or CSAFE. Okay, so a quick outline. I'm going to start with a motivation, motivate the problem of statistical approaches to forensic evidence, using DNA analysis, and then show kind of where digital evidence is lagging behind. I'm then going to formalize this notion of quantifying strength of evidence, apply that method to geolocated event data, and then finish up with future directions and conclusions. Okay, so let's start with some motivation. Okay, so say we're at the scene of a crime, and police recover two different types of evidence, the first being a cell phone and the second being a DNA sample. They take this evidence and they hand it over to a forensic investigator. The forensic investigator is tasked with analyzing this evidence and coming up with some objective summary of its probative value. So she's going to start with the DNA evidence because she has a very well-defined process for analyzing DNA evidence, and it's very familiar to her. Typically, this process involves, taking the crime scene sample, denoted by this bar here, and obtaining samples from suspects in the case. So each of these bars, each of these vertical bars represents a selection of a genome, and these horizontal bars within them represent allele expression at a particular location along the genome. So, right, the black bar represents expression of a gene, and a white bar represents the gene not being expressed. Okay, and so basically what we're going to be doing here, what the forensic examiner is going to be doing, is taking the crime scene evidence and comparing it to each suspect sample one by one. Typically, the first step here is to assess the probability of observing the crime scene sample and the suspect sample, assuming that the crime scene sample is generated by the suspect, so assuming that these are from the same person. And in DNA evidence, this is pretty straightforward. Either the DNA matches or it doesn't. So in this case, this would be a value of 1 for suspect number 2 and 0 for suspects 1 and 3. Really, the important piece for DNA evidence becomes the second step, which is assessing the likelihood of observing the crime scene sample and the suspect sample, assuming that they're from different sources. And some assumptions here that are made are that alleles at different locations along the genome are independent, and that we have a database such as CODIS, the Combined DNA Index System, that can give us an estimate of how frequent different alleles are at different locations along the genome, and allow us to estimate this probability. This is referred to as the random match probability. So basically, how likely was it that some DNA sample could be generated by any person randomly in a population of relevant individuals? The investigator then takes these two probabilities, 1 and 2, takes their ratio, and computes this quantity known as the likelihood ratio. When this value is less than 1, it indicates that the two samples, A and B, the crime scene sample and the suspect sample, are from different sources. When it's equal to 1 or near 1, the result would be inconclusive, right? That the evidence provides no value as to the source of the unknown source sample. And then when it's greater than 1, it indicates that the samples are from the same source, right? So that the suspect was, in fact, the person who generated the crime scene evidence. But going back to our crime scene from before, we kind of have this problem. One of the police officers was eating a donut and contaminated the DNA evidence. We had to throw it out. So now the forensic investigator turns her attention to, the mobile phone. And this process really applies to a variety of different types of digital evidence, right? So this could be mobile phones, it could be computers such as like notebooks or desktops, and it even could be from the cloud. And she has a suite of tools available to her for taking these devices or the cloud and extracting out relevant data. So this could be things like browser requests, web searches, GPS locations, file access activity and network activity, etc. Given the data extracted off the device, there's also tools that she has at her disposal for analysis and visualization of said data, right? So This could be things like interactive timeline analysis, where basically she's trying to reconstruct a sequence of events that happened on a device around the time of interest, around the time of the crime. So here I have a few examples here where it could be looking at timestamps of different events over time, or like geolocations of different types of events over time, etc. But what's missing here is how to take this data that's been extracted off the device and analyzed and put into a clean format, and form probabilistic conclusions regarding source, right? So for example, how do you compute a likelihood ratio for digital event data? And that's going to be the focus of the DFRWS paper that I'm going to be talking about today. Okay, so in the next part of the talk, I'm going to take some time to formalize this notion of the likelihood ratio and then apply it to digital event data. Okay, and in general, this formalization of the likelihood ratio falls under statistical approaches to evaluating forensic evidence. Okay, so what's our goal? Well, our goal is to assess the likelihood of observing our evidence, right? So here our evidence is defined by the crime scene sample and the suspect sample, under two competing hypotheses. So the first is that, the person who generated the crime scene data is our suspect, and the second is that the crime scene data was generated by someone else in a relevant population than our suspect. All right, so to formalize this, we're going to refer to the unknown source sample as A, and the known source sample, or the suspect sample, as B. And we're going to be, assessing the likelihood of observing A and B under two hypotheses. The first is H sub S, A and B came from the same source. And the second is H sub D, that the evidence AB came from different sources. Okay, but at this point you might be saying, wait, Chris, why aren't we interested in the probability of the source hypotheses given the evidence, kind of flipping this thing around? And here what I'm referring to is the statistical notion of a posterior odds, right? So what's the probability that the crime scene evidence was generated by our suspect, given the values of the evidence, A and B, compared to the probability that, the suspect did not generate the crime scene evidence, that they're different sources, given the data A and B. And you can use a very well-known concept in statistics. It's known as Bayes' theorem. To re-express this posterior odds as the product of something called the likelihood ratio, that's what we presented before, times the prior odds. And really, this is where we kind of can see why a forensic examiner does not present a prior odds, but instead presents a likelihood ratio, because the prior odds here is subjective. And the goal of a forensic analysis is to provide an objective measurement of the strength of evidence. Okay, so really what we have here is that the jury holds the prior odds. So, the prosecution and the defense present information in a case before a forensic examiner comes up and presents the evidence. And they form opinions while hearing all this. Like, so how likely is it that the suspect is guilty versus not? And then the forensic examiner comes in, presents the likelihood ratio, which is an objective measure of how likely it is to observe the evidence, given if the suspect generated it or in fact it was generated by someone else. And the jury then uses this numeric value to update their prior odds and form their posterior odds, and they can go on to make a judgment for guilt or innocence for that particular suspect. So our focus then really is solely on this likelihood ratio. And that's one such way to measure the strength of evidence or weight of evidence. I'll use these terms interchangeably throughout the rest of the presentation. So the likelihood ratio is widely accepted as a logically defensible way to assess the strength of evidence. It's been applied in a variety of forensic disciplines, including DNA, fingerprints, handwriting, and speaker recognition. There's been many studies that demonstrate its understanding, both common misconceptions of lay jurors, as well as verbal equivalence. Instead of expressing a numeric value, there's ways to express the likelihood ratio on verbal scales. Okay, so that's great. Now you might ask, why wouldn't we always just use the likelihood ratio? Well, there's many reasons. One is the complexity of evidence, particularly for pattern evidence that tends to be images. This could be like shoe prints, images of shoe treads, or blood spatter analysis, images of blood patterns on the wall. And then digital evidence, is kind of this other realm where, there's potentially a high number of different dimensions corresponding to different types of data residing on a device. It's really, the dimensionality is exacerbated here in digital evidence. Not only that, but feature selection is also a problem. There's a wide variety of features to consider. So a good example here is in fingerprint analysis, minutia, or like characteristic features of fingerprints. The more minutia we have of a print, the better our numeric summary of the evidence can be, the better the likelihood ratio can be. And this problem, again, is exacerbated in digital evidence where, do we consider just like file access events, or do we consider like the geolocation of the device, or network traffic on the device, etc. Not only that, but developing appropriate probability models is difficult. You must describe variation both within a given source, under the same source hypothesis, and between different sources. This is the different source hypothesis here. And then finally, you have to have some sort of reference population to rely on to estimate the parameters in these statistical models. So, for example, the CODIS system for DNA is very useful in formulating likelihood ratios. Okay. So an alternative approach I'll just briefly touch on is known as the score-based approaches. So instead of looking at the data A and B directly, you instead look at some summary measure, delta, which is a function of A and B. So this is typically just like some distance function between two samples, for example. And then you assess this function over known different source pairs and known same source pairs, and basically compute the ratio of these at a new value. So here we have like a distribution over different source pairs, distribution of delta over different source pairs, distribution of delta over same source pairs, and then for new evidence whose score is equal to little delta, you simply just take the ratio of these two points, and that would be your score-based likelihood ratio. Okay, this is gaining popularity across a variety of disciplines, including speaker recognition and fingerprints and handwriting. Okay, so we have two techniques to evaluate evidence, the likelihood ratio that models evidence directly, and the score-based likelihood ratio that models some low-dimensional summary of the evidence defined by this score function delta. And today I'm going to focus solely on the likelihood ratio. Okay, so let's talk about quantifying strength of geolocated event evidence. And here what we're going to be looking at is in some bounded regions. So here we have Manhattan Isle in New York. Our data now, our evidence becomes sets of locations in this region, right? So A, for example, would be the set of black points that are locations of some type of event occurring on a device. And then B would be some other type of locations of events of some different type or some different time period. And we're interested in determining how likely it was that the same person generated the black points and the red points here. And a little bit more concrete example, geopoints warrants are starting to gain popularity. So assume that we have some sample of locations defined by these black circles A, and it's the same in both of these plots. These black circles could be locations of interest from a given device, or they could be locations of different crime scenes. And what investigators will do is they'll draw boxes around these points, and they'll ask a service provider, such as Google or an internet service provider, give me all of the accounts that have generated events within one of these boxes in some given time period. And so here, these two plots, what I've shown is two different accounts that had hits in a geofence defined by these green rectangles. And the question now becomes is, what's an objective measure of the strength of similarity between the red X's and the black circles, and then between the blue triangles and the black circles? And now we're going to use the likelihood ratio to define that relationship. Okay, so let's revisit the likelihood ratio. Remember, it's the probability of observing the evidence under the same source hypothesis divided by that same probability under the different source hypothesis, right? So here A is going to be our unknown source events, those black circles, and B is our known source events from a suspect, right? Those red crosses, for example. And you can do some math and reduce the likelihood ratio down to this conditional expression that I have up here on the right. And I think it's just easier to look at this through examples and images. So let's look at that. So the likelihood ratio can be written as the probability of observing the known source events B, right? So the locations of these red X's, given the locations of the unknown source events A, so these black circles, and assuming that the person who generated the events in A is the same as the person who generated the events in B. Okay, then the denominator of the likelihood ratio is just going to be the probability of observing the known source events B, these red X's, assuming that it was generated from someone else than the person who generated A. And this is basically a random match probability. How likely is it that you would observe events at these locations across a relevant population? So that's a little bit easier to define. Let's start there. Remember, in DNA analysis, I said the random match probability was, how common alleles are at specific locations along the genome. Now what we're going to be interested in is how common events are at specific locations in space, right? So for example, we have Orange County, California down here on the left, and Manhattan up here on the right. And this is an adaptive bandwidth kernel density estimator. The details of this aren't really too important, but the basic idea is that for very common locations such as Disneyland right here, along the beach, or near like Broadway and Hell's Kitchen in Manhattan, you have a very high likelihood of an event being generated there versus areas like in Crystal Cove State Park or parts of Central Park that are less likely to be frequented at random in the population. Okay, so that's going to be our random match probability, the denominator of the likelihood ratio. So now let's turn our attention back to the numerator, right? So we're interested in the probability of observing known source events B, assuming that we have some set of locations A that were from the same account, right? So what we do here is something called a mixture of kernel density estimators. And the basic idea is that new events are highly likely to occur near previously viewed events within the same account. Okay, so the idea here is this contour plot down here on the left refers to an individual component or an adaptive bandwidth kernel density estimator built on the locations in A, where here I have the red X's are the event locations of B superimposed on top of that. So the idea is that if A and B came from the same source, you expect a high likelihood that in the future they'll revisit areas they've already been to in the past. Okay, the second part of our mixture is going to be a population component. So this is the same thing that I introduced a few slides ago. For the denominator of the likelihood ratio, this is just, where are we seeing events across the population in general? And then finally, we're going to define our numerator of the likelihood ratio to be a mixture of these two, right? So in this example, we have 80% weight being placed on the individual component and 20% weight being placed on the population component. So the idea here is that, about 80% of the time, roughly, we're saying that, new events from the same person will be generated nearby in space to previously seen events for that person. And there's some chance that they'll go visit new areas in the region that are popular, such as like Disneyland or like the airport or the beach. Okay. So we're back to the likelihood ratio here. We can now express this as the ratio of two statistical models. The numerator is that mixture model that I just finished introducing, right? So this mixture model with weight placed on previously seen locations in the unknown source sample, and then the denominator is simply just a population model. How likely is it to see these events in particular locations across a population? Okay, so let's revisit our geofence warrant example. Looking here on the left, we have our unknown source data A and our known source, our first known source B1. The likelihood ratio here is approximately 1,137, which would indicate strong support for the same source hypothesis. Where on the other hand here, the second sample, B2, the likelihood ratio is near 0, and this would result in an exclusion, right? So the person who did in fact generate these events was known source B1 and not B2. Okay, so now we can think of performing a case study here where we get basically a large sample of both known same source and different source pairs, and we apply the likelihood ratio to each sample and get an overall kind of error rate estimation across these samples. So it's very hard to collect a lot of realistic case data, as many of you may well know. So as a surrogate, we collected data from Twitter in 2 regions, both Orange County in California and Manhattan in New York. And then we defined A and B to be all of the events in an account in 1 month. So month month 1 is set A, and month 2 is set B. So it's 2 consecutive months. All the events from the same account are A and B. In Orange County, we had about 7,000 accounts. In New York, there's about 13,000 accounts. Those define our same source pairs, and then the different source pairs are defined by a stratified random sample. So in both Orange County and New York, we did a random sample of 9,000 different source pairs, and then we used these samples to estimate overall error rates of the method. So here I'm just going to show a selection of results from the paper, both for the likelihood ratio method that was presented today, and then for the one of the score-based likelihood ratio methods we investigated as well. That we did not have time to discuss. But basically what you see here is that the likelihood ratio has a very low false positive rate. So not very often do we make a mistake saying that two event series were generated by the same person when in fact they weren't. But you suffer in terms of true positive rates, so the sensitivity isn't as good as compared to the score-based likelihood ratio. And I think more interestingly, if we focus on the false positive rate as the amount of data in the sets, as we get more events in A and B, our false positive rate actually decreases in both New York and Orange County, and regardless of method, right? So either if we're using the score-based likelihood ratio or the likelihood ratio, as we get more data, our error rates go down, which is good. Okay. So briefly talk about some future directions and a summary of what I presented today. So I think there's 2 primary areas for future work. The first, we need to start collecting and sharing relevant digital data amongst both law enforcement and researchers. For example, we want to build a CODIS-like database for digital event data. This will facilitate research, make it easier to baseline methods and compare them, etc. Second of all, given that we have some database, using a method like this for discovery, I think is a very interesting application, right? So say law enforcement has some sample that they're unsure who the suspect could be, if they could upload that sample to some service that would then return like, hey, here's the top 10 most likely suspects as far as matching on the geolocation methods that we talked about. And, doing this very quickly to aid in investigations. Okay, so in summary, I talked about how statistical approaches play a key role in the forensic analysis, of a wide variety of evidence with the DNA as a gold standard. And digital evidence is somewhat lagging behind other forensic disciplines in regards to statistical approaches. And then I presented a framework for estimating likelihood ratios for geolocated event data. And with that, I thank you for your time.